Okay, so today what we're going to do in class is cover this thing called a PyObject, which is the core Python object that kind of underlines everything. We've seen this before in the past few weeks, but we never really gone into it. So if you remember, if you look over all the C code in the interpreter, there's a bunch of PyObject stars everywhere, right? There's a bunch of pointers to PyObjects, and today we're going to finally talk about what that is. I purposely haven't talked about it until now because you've been able to kind of gloss over it when you're doing the first assignment. So the learning objective today is to be able to inspect any object in Python and understand the basics of its inner contents. And last time we covered frames, function calls, and basic scope. So that was last time's lecture, and this time we're kind of taking a little detour into the Python object. So today what we're going to do is we're actually going to do a really fast review of the first 2 weeks, and it's because we have 2 new students here. It won't be enough to get them all caught up, but just at least as a starting point so they can go over it offline. This is actually going to be a good review for everyone else as well, because just to reinforce the concepts. Then we're going to go over the Python data model, which is the idea that every piece of data in Python is some kind of object, quote unquote, and then this Python object protocol, which is the methods that all objects have to implement. And then we're actually going to go into the code. The relevant code here is include/object.h and object.c. So you can pull those up now if you want, but we don't have to worry about it just yet. So the first thing we're going to do is we're actually going to review. So for the review, we'll actually just use the assignment, the code from the assignment. So we'll have you two look over it offline also. So basically what the assignment says with the 2 new students is to trace all possible executions of the following code through the main interpreter loop. And this is a piece of code here. I just wrote it out. Here in my terminal, test.py. These are line numbers on the left. So there's a piece of code, assuming you have some numbers x and y, which we don't have yet. If x is less than y, we assign z to be the value of x. Else, if true, which always happens, we assign z to the value of y. Else z equals 100. So this z equals 100 will never execute. So either this thing happens or this thing happens. So do you have a Python prompt running, or you can run Python, right? So can you create some test.py file with this contents? Well, you can just copy it from the course webpage also. It's just this if x less than y thing. I just want to make sure you can run it. Yeah, just edit it somewhere and try to run it. Here, I'll keep the code up here on the left so you can see it. But for everyone else as a review, if you actually try to run it, something bad happens because you didn't actually define x, right? Like this code isn't actually runnable because nobody cast you x or y. But just because it's not runnable doesn't mean you can't actually compile it. It still compiles. So do you have this up? Yeah, we're trying to still go. So this is Windows. Okay, so you need to actually, do you have a command line, a terminal here? Okay. Yeah, just do CMD on Windows. So you need to, yeah, and then type Python here. See if you actually have Python. No, you don't. Open up the Python command line and see what happens. It's harder to set up on Windows here, so go to that one. Okay, it's not gonna work super well, but okay. Well, you'll just have to watch along because you can set up the Windows environment later on. So one thing you can get on Windows is this thing called Cygwin, which is and this Cygwin provides you with a Unix-like environment on Windows. So you can download that offline. That's what I would recommend if you're on Windows. It's just a lot easier. Or you can SSH or log into a Linux or Mac. Because the default Windows command line working in Python is not great. So this is Cygwin. Basically, it looks like a Linux or Mac shell, but it's actually, I have Windows right now. It's actually running in Windows. So the basic gist of this is if we actually run Python-mdis with test.py, this runs a disassembler. So what this command does is it actually compiles the Python code but doesn't run it, and it prints out the bytecode in a nice kind of human readable format. And basically what happens in as a really high level review in Python is actually we'll just write it in here as a super high level review for everyone is that you start out with a source file, something .py. That's Python source code. When you actually run Python, what happens is that this first goes through a compiler. It's a very simple compiler, and then it turns it into what's called bytecode. And then the bytecode is run by this thing called the Python interpreter, and then it outputs, some output to your screen. So that's the very high level view of everything. So when you actually are running Python, it actually does both of these steps at once behind the scenes for you. So there's no separate that's why people don't normally say Python as a compiler, even though it does, because the compiler interpreter runs all together. But the interpreter actually works off of this thing called bytecode and not the source code itself. So the purpose of this class really is we're going to skip over the compiler part and assume that it works and that it just transforms these .py source code files, which is in the Python language, into a bytecode, which is a different language, which is a language we've been studying the last 2 weeks. And we're going to look at these bytecode files because these bytecode files are exactly what is fed into the interpreter and to give the output. So the interpreter is all written in the C language, and it's a bunch of C, .c and .h files. And what we've been doing the first 2 weeks was tracing the execution of a simple Python program through the interpreter and seeing how the interpreter actually implements this. Okay, so we're going to focus on this bytecode thing now. So what this bytecode says is, you all can look at this offline, is every instruction kind of corresponds to one thing the interpreter executes. So the interpreter conceptually just walks down one bytecode at a time and does something. And then if there's some kind of a jump condition here, so this says pop jump if false. So that means that if there's a false, we're going to jump to 21, and 21 is here. Otherwise, we're going to keep going straight. And this is where there's actually a branch in the code. So it either goes straight down, or it actually directly jumps here. And then there's another pop jump if false. So this goes to 36, or it could go to 36, or it could keep going down to there, and these keep going down. So the execution kind of flows linearly unless there's some kind of a jump, in which case it jumps. So if you're familiar with, say, assembly language, this is pretty much, bytecode is pretty much assembly language, but it's kind of nicer, and it's being run for Python. So each one of these bytecodes is called an opcode. So each one of these has a specific meaning, and you can look it up in, if you look up the documentation just look up Python bytecode online. Oops. Python bytecode on Google. So all these things you can just click on Google. The first thing is called the disassembler, which is the module we saw. And we're going to use, by the way, in the class Python 2.78. We're using Python 2.7. And if you actually scroll down documentation, you can find all the Python bytecode instructions and what they do. So an example is binary add is a bytecode. And what this says is that it implements the top of the stack equals top of the stack 1 plus top of the stack. So all of these things are just instructions, and you can study all these offline. And conceptually how the bytecode works is that there is a stack of values that is being kept at all times. So I'm going to actually show you the bytecode. We're just going to step through the bytecode with the source code once, just so you can see it and you can study offline. And to review for everyone else also. Let me open up a new browser or new terminal. And let's see. Okay, so test.py. So recall our source code is to the left and the bytecode is to the right. And I just want to illustrate this graphically. So notice the source code has 6 lines, right? And the bytecode has a corresponding thing for each line of source code. So this says 1, so that's line 1. This says 2, line 2, line 3, line 4. There's nothing on line 5 because it's just an else, and line 6. That makes sense? So each line of source code conceptually compiles into more than one line of bytecode. That makes sense because the source code is more compact and high level, right? The bytecode is like an assembly language, so it has to expand more. So this step is the compile step. So what the interpreter does is conceptually, if you're thinking about how to execute Python code, you just step through one step at a time, right? You go here, is x less than y? If so, let's go here. Otherwise, we go here. And then it's always true, we go here, we jump over the else, and we're done. So the interpreter basically does the same thing, except it doesn't work off of the source code because it doesn't know about the source code. It works off of this end, which is the bytecode. So conceptually, let's just step through this. So recall that the Python bytecode interpreter has a stack of values that it keeps at all times. So we're going to have the stack just grow down because stacks growing down looks good. So let's say that x is, let's just say for sake of argument that x is some number 10 and y is some number 3, just for this program. So when we first go to this first line of bytecode, it says load name x. What this means is that it means to load the value of x onto the stack. So after we execute this line, the stack should have 10 on it. It doesn't have x on it, it has 10 on it because load name actually loads the value. These things are just names. The boxes are actual values. This actually be relevant to everyone else because the boxes are all PyObjects, which we're going to study this out. So when we execute the second line, load name y, it just again pushes the 3, which is the value y, onto the stack. So the stack again goes downwards. Okay, so far so good. And now the next thing it executes, again, the interpreter is really dumb, right? It's very naive. It just keeps walking down and does one thing at a time. It's a compare operator. And if you look at the documentation for compare operator, it says that this kind of compare operator is a less than comparison. And it corresponds to this line of code. So remember, all this is happening in line 1 right now. The interpreter is very, very naive. It just says, let's load x, let's load y, which we're here. And then now let's do a less than comparison. So the compare operator, notice it only takes as an argument the kind of operator. It doesn't have to say x is less than comparing x and y. And it's because all the operations in Python use the stack to operate on. So that's why we had to push 2 things onto the stack before we compared them. So the comparison just knows I'm going to take the first 2 things on the stack, compare them, and then return a value right on the stack. So this is actually false, right? Because x is not less than y. So this comparison returns false. And the result of running this line right here is that these 2 things get popped off the stack because we're already done. And we're going to push an object called false onto the stack. Does that make sense? Okay, so now after this line is run, there's only one thing on the stack, and it's an object called false. Okay, so now we're going to go to this step, which is pop jump if false. So this is an opcode. Again, you can look at the documentation. This says pop the thing off the stack because we don't need it anymore. And if that thing that we popped off is false or a false object, we're going to jump. And where we're going to jump? We're going to jump to 21, which is the instruction number. 21's right here. And there's a little arrow because it means that it's a jump target. You can jump to it. So we're going to pop it off. So pop, this thing is gone off the stack. It is false. So we're actually going to jump. So now our interpreter actually jumps down here. So it skips over all the rest. So that is the equivalent of running this line of code and then jumping directly into this line of code, right? We jump directly into line 3, into 21, right? It's getting a little bit messy, but we jumped directly into 21. So we skipped over all this line 2 business. So again, we compared and we jumped directly down here. So this line 2 was never executed, at least in our current execution. Okay, so now we're here. We're going to load name. And what are we loading? We're loading an object called true. And the reason why we're loading a true is that this is just a true constant. So we're going to load it on the stack, which pushes true onto the stack as an object. And notice how there's no comparison or no operation here. This is a really silly statement, right? It just says we're going to load the object true, and then else if true means let's just do an if statement again. Is it true or is it not? So again, this compiles into a bytecode called pop jump if false, the exact same bytecode. And this pops it off the stack. Now it's gone. Now we're not going to jump now, right, because this thing is not false. So we're not going to jump, and we're just going to keep moving to the next line. So this line is actually line 4, if you notice, right? So this line is inside of this if now, right? We've actually taken it and gone inside to z equals y. Okay, so now we got to do this code, z equals y. So what is z equals y? It's this stuff right here, which is load name, which loads the value of y into the stack, and y is still 3, so we're going to load 3 on stack. And then store name into z. So store name, what it does is that it pops the thing off the stack, and it assigns it to a value z. Yeah, so let's put z here. So it points to 3. So it pops it off the stack, and so load name and store name are complementary. Load will load it onto the stack, store will take it on the stack, pop it off, and store it into an actual name in your program, which is z is 3. And then this jump forward means we're always going to jump unconditionally to 42, which is this one. So we jump all the way to this one. And then this is just the end, the end of the program. So then the program says load constant, none, which means load a none object onto the stack. Notice how you have no code to say that. There's no code that corresponds to this. This is actually not line 6. Line 6 is actually here. This is actually just some empty thing at the end of your file that is automatically inserted. There's no line that says load none return. But if you're familiar with Python, if you don't return anything from an object, from a module or from a function, it will return none. It's just a special none object so that every function returns something. So what return value does is that it pops the thing off your stack and just returns it to whoever called you. So this actually doesn't do anything. So this is a very, very high level overview of how Python execution worked in this case. So for your, this is actually the assignment that everyone did in the first 2 weeks. So we'll talk to you two offline about what we can do about that. But this is a very, very high level overview, but you'll have to study it on your own. Okay, cool. So getting into the main event of today is what we're going to do is we're going to look over the Python objects. Cool. So we got, okay. So so recall my example here. Everything is an object, right? So what is this object business? So in Python, if you actually go, let's just go to the terminal in Python, the prompt. So everyone can just, whoever has a working laptop can just open a prompt. This Python. Oh, so you can actually do this now because you just open the Python command line. So before you couldn't run it because you have to run the file from the shell. Now when you're in Python, again, you can type whatever you want. X equals 10, y equals 3, x plus y, you know, z equals x plus y, z. It's just like Python. So remember there's a special command in Python called dir that when you call it with something, with an object or anything, it'll tell you what's inside of it. This is what's called inspecting the object. So dir is a function that you call on anything, and it'll tell you what's inside of it. So this is what I mean by okay, so we reviewed this, good. This is what I mean by inspecting, what is it? Inspect an object in Python. So we're going to talk about this Python data model now, how everything is an object. So recall that in a language like C or Java, the primitive data types, like an integer, for example, isn't like an object, right? It's just a piece of data that's represented by like 4 bytes or 8 bytes or whatever in your machine for efficiency. So when you have in C, when you declare an int x, or in Java or whatever you declare, you know, long x or whatever, that actually allocates memory for however many bytes the integer or the long thing is. And it just directly stores and loads stuff from that memory. When Python, it's a little bit more complicated, and it's because in Python, the model in Python is that everything is an object. So even a number like 1, 2, 3, it prints out as a number and it's stored. Yes, there's some numeric representation 1, 2, 3 in it, but actually that's actually wrapped in a big, you know, it's wrapped in a big veneer of an object called a PyObject. So everything in Python, every object is this big, is this big PyObject thing. And it so happens that this is a special kind of PyObject called a, I think it's called a PyInteger. I don't actually remember the name, but we'll look at it later. And it so happens that inside there's actually a 1, 2, 3 inside. But it actually has a lot of other data in every PyObject to keep track of operations and things. So this is less efficient, obviously, right? It's less efficient than the C or Java counterpart. But it makes things a lot more flexible because, for example, if you wanted to, for some reason, override the integer type to do something different, you can just override the integer type and have your special integer act as an integer, or your special string act as a string, or so on. So it kind of, this is one of the hallmarks of these dynamic languages like Python or Ruby, is that because everything in is object, you can override anything you want, more or less. So you give up stuff in efficiency, but you get more flexibility. So for example, if I just say dir on 1, 2, 3, okay, so you notice how dir on 1, 2, 3 itself gives you a bunch of stuff. It gives you a bunch of fields inside that object, or things you can do to it. So what are all these things? All these things are actually either properties or methods you can call on the object. So let's see if we can do this. You can't do that with the literal. So, okay, well, let's do, in Ruby, you can do this. So let's say x equals 1, 2, 3, and then dir x. Okay, so x is it has some stuff inside. So in Python, one of the conventions is that things that have double underscores in them are special kind of fields or properties that have some special inherent meaning. And a lot of these, what they mean is that they actually are special operations that you can do on objects. So for example, add, divide, multiply, negative, comparison, all these things, if you try to squint at it, you might be able to guess what they do. So the add method is just a thing that allows you to add two things together. So for example, if I say x dot underscore underscore add, this is simply a method. It's just a method just like any other one. And if I call it x dot add on what is it, x 1 2 3, let's add 1 to it, and it gives us 1 2 4. Does that make sense? So all this is that it's just a method that when you call it, it does the addition operation and gives you a new object back. Now this is the exact same thing as saying x plus 1.
It gave me invalid. Oh, that's okay. It's no one. Okay.
Was there a question or confusion?
It gave me invalid syntax, and I realized that.
Use a literal, right? Did you use a literal or what?
Yeah.
So you can't do this in Python, which is
right.
In Ruby you could. In Ruby you can do that, but in Python I guess you need to have the variable like this doesn't parse because Python doesn't. Oh, sorry. Python doesn't let you call a method on a literal or something. Mm-hmm. So how do we know what all these operations are? You can look up this thing on today's lecture. There's a thing called. Let me go to schedule. There's a thing called the Python data model. I'm just going to open it. Did that work? The Python data model. This is a really long reference. You don't have to read it all. But basically what this says is this tells you how Python objects are represented and what you can do with them. So you can read over all this offline. But basically what this says is this says is emulate numeric types. So all these methods, such as add, subtract, multiply, divide, modulus, power, shift, and, or, XOR, what these methods are is that they're called when you're doing arithmetic on stuff. So when you actually do something like x plus 10, this thing is actually, what this is implemented in Python itself is it knows that there's an addition operator. So what this actually translates into is x dot add 10. It actually calls a method on an object, an add underscore add method. So it just so happens that all the integer objects, their underscore add method just implements an integer add. So let's actually look at this. We're skipping it a little bit, but let's actually just look at it to convince you this is the case. So we're going to go into the Python code. Let's look at objects and look at int objects. So in Python 278 objects, int object. So int object is the object that represents an integer. So I'm going to try to find where the add is. Add. Yeah, there we go. Perfect. All right, so this code looks like super complicated and weird for just adding, but this is essentially what it is. So this method is called, this int add method ends up being called when you're adding two integers together with the plus operator. Now every method, so notice how this method takes a PyInt object, pointer to it, another PyInt object, a pointer to that, and returns a pointer to a new object. So it does what you think it would do. It would take the two integer objects, grab their integer parts out, add them, and then return a new object that has the new value in it. So so in C here, in the interpreter, these are all longs because I guess integer represented as C longs for more space. Convert to long, convert to long. I assume this is a macro that actually takes the object, V and W, and stuffs it into A and B as the actual long representation, and then cast a line below a more undefined behavior. So when you're adding stuff, there is some, crazy stuff with overflowing, and then the final thing is it returns some crazy thing here, which x equals long. Where's x pi? Oh, okay, sorry. So the this is a different case. So this is the common case, right here, I think. So the common case is x equals, we're actually going to add a and b. There's the integer addition, and we're going to stuff it into integer x. And then if some case holds, like the overflow, I haven't thought about this enough to know what this actually does, but I think it's just checking some overflow behavior. If this is legitimate, we're actually going to create a new PyInt from long. What this method does is it takes a long, which is a C long integer, and it creates a PyInt object from it. So it actually wraps it up into a PyInteger object, and then it returns it. So this is pretty elaborate when, like, in C, all you do is say a plus b, right? And in something like C or Java, it literally just says a plus b. But what this does in Python is that it actually unwraps the two objects v and w. So v is here. It points to some big object that's a PyInt object. Inside of it, there's some number called like 1, right? That happens to be a number. W again points to some big PyInt object. Inside of it has a little thing called 2. And what this method does is it pulls the 1 and 2 out. It adds them together to make 3. And then it creates a new big thing out of the 3, a new box around it, and then it returns it to its caller. Right? So that the interface in Python is that we're always working with PyObjects. Everything has to be wrapped in a PyObject. So if this seems obscenely inefficient, it's because it is, right? Like that's why a language like Python is much slower than a language like C or Java, because every operation has to go through this unboxing or boxing procedure. So if you're familiar with Java, there are, let's say like a big integer type or some special numeric types that actually go through the same process, whereas the primitive integer types in Java don't go through. But in Python, everything is an object. So that's how it works for integer types. So the basic principle I want to illustrate here is that everything operates off of these PyObjects, and there's a C file that implements every kind of PyObject. And we'll go over this next time, but if you look at objects, these may seem pretty standard, right? So there is a int object for integers, there's a list object for lists, a set object for sets, a string object for strings, that seems important, a tuple object for the tuple types, dict for dictionary, and so on, float object for floating point type, and so on. So there's an implementation for every single type of object, because the interpreter needs to know about it. But as far as you're concerned, when you're writing Python code, you don't ever have to say x.add__add, you can just say x plus 10. So this is called the Python object data model because this is what you can implement when you create your own object. Let's say you're working on a project where you have to represent points on the coordinate plane. Then you can create a class point and create point objects out of that. And if you want to say compare 2 points, x is less than y, what does that mean? Maybe it means that it's closer to the origin. Maybe it's a polar coordinate. So maybe your point comparison could be, if x is here and y is here, maybe x is less than y or whatever is comparing their absolute magnitudes, how close they are to the origin. Maybe x less than y is comparing how high they are from the y-axis or whatever. Like, you can define it. But the thing is, if you make your point class and objects right, and you implement these certain behaviors, then you can just say something like, you can just write x less than y in your code, and Python will actually look up the method that implements this for your particular class. So there's a bunch of stuff here. There's additions, there's comparison. So there's this underscore CMP, negative, coercion. There's just a lot of stuff. So actually, the CMP is, let's look up CMP. Rich comparisons. So if rich comparison not defined. So remember how there's that like comparison code we saw last time? This is the most general case. It actually just calls the CMP operator. So when would you use this add? You use add. Sorry, let me grab this. So, for example, if I made a point class, which is actually just like a really vector class, if x is this point here, 3, 3, and y is a point -1, -2, what should x plus y do, right? I don't know. It depends on what your class is. Maybe it's a vector addition, right? Maybe x plus y, you implement the __ add method for your point class so that x plus y actually adds these two and then adds these two and then returns you a new point with their with that coordinate. That's one very reasonable way to say x plus y. It could also mean something completely different. And so the idea is that these overloaded operators, it's really up to you to implement. And all you have to do to implement them is just to create an object that implements these methods. So, the high level thing about Python objects is that they all just communicate through this interface, which is called the object, the data model. There's actually a ton of stuff here. Okay, so the second half of it, this whole thing, endeavor, is this thing called the object protocol, which is the C API. So the object model, data model is all in Python. This is all the Python code you can possibly write to interface with objects. Actually, let's do a little bit more of this before we go on to the C one. So all objects have certain properties in them. This won't go up. So every object in Python shares certain properties in common. The one property is called ID, which we saw earlier. So if ID of x is number. So what do people think this number is? Let's say y equals. Yeah. So one thing is it could be a hash key. The other thing, I think the way it's actually implemented is actually just the pointer value. It's just the memory address. So if you notice how when x, well, let's do another example. They're different because they're different numbers. So ID of x and ID of y. ID is just some unique ID that represents this object in memory. And in the CPython interpreter, it's just the pointer value. It's just the address in memory. And the Python interpreter guarantees that once an object is allocated that address, it never moves. So that address is good for the lifetime of the object. Of course, if you destroy the object and you create a new one, it might actually have the same ID still. So it actually shouldn't be a hash. Right? It should not be a hash because it's just the memory location. It's probably not good to use it as a hash. ID is one property that all objects have in common. We can look at some other ones. So today's lecture is going to be purposely generic because I'm trying to talk about all objects as a whole, because each individual kind of object has its own quirks and fields and stuff. So I'll go up on this and all the way up. So here is what's mentioned. Every object has an identity, a type, and a value. An object's identity never changes, so use ID and use types. So you could read all about this. So type is the other thing. So type is another function. Type x is an integer. Y we can make into a string. Type y is a str is a string. Z is a list. Type z is a list. So every object not only has a ID, it has a type. So we can imagine now what a PyObject actually looks like. So a PyObject must have certain things in it. It must have a type that points to some kind of type, right? This thing could be a string or an int or a list or something. Every PyObject has to tell the world what type it is. It also has an ID, but I don't know if it actually needs to store that ID. We'll see it because you can just calculate it from the memory location. But it needs to conceptually have an ID, right? It needs to have some ID, have some type. What else do all objects need to have? It needs to have a value, so it needs to have some kind of a notion of a value. So I think those are the three things in the protocol. So this value is either a real integer. It's either a string in memory, like blah 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 string. It's either a list of something in memory. It's something, right? So every PyObject has to have a type, an ID, and a value. And this is just the very basic. So notice how this has nothing to do with the kind of object, right? An integer object is like this, a string object's like this, a list object like this. Everybody is like this. And yes?
This has the reference.
Good. Very good. Very good. So the reference count is also inside the PyObject. Very good. So the reference count was not mentioned in the data model because it's not part of Python itself, right? This is part of the internals, but actually right here. Very good preempting right here. So the CPython implementation detail. In the CPython implementation of Python, it uses a reference counting scheme for garbage collection. So this is something you two will have to look into yourself. But basically what this says is that every object, sorry, this is hard to read. Every object has a reference count inside that tells the system how many things are pointing to me at this point. So every PyObject has a reference count inside. It's very good. So for example, if I assign the name x to this PyObject and I put an arrow to it, I need to actually increment the reference count to 1 because one thing is pointing to me. If I now assign it to y, I need to increment the reference count to 2. If I now assign it to z, I need to increment it to 3. Now if x gets deleted or reassigned to something else, I go back to 2. If y gets deleted, go somewhere, we go back to 1. When z gets deleted, I go to 0. And when an object has a reference count of 0, it's garbage collected, which means that the Python system knows that we can delete this object. And we know nobody's actually holding a reference to it. Good, so the reference count is definitely part of it. Let's see if we can actually get the reference count out from Python itself. I don't think we can, but let's try how to see. That would be accurate. There's a GC module, so bear with me for a second. I don't think we can, but let's see. Oh, I don't think so. So there's a GC module in Python that does manual garbage collection, but Python has an automatic garbage collector, so you don't have to do this manually. But there are some cases where you want to run it manually, but I don't think you can do the reference count. But I'm gonna just bear with me for 1 second while I see if I can figure out how to do reference count. So Z is a list. So ID is there. Reference count Python. I don't think you can actually access it. I don't think they make it accessible in Python, but in the interpreter you can definitely see it, right? You can query the reference count. So Python reference count query. Have a type of reference. No. There we go. Look at that. Someone asked. Oh, get ref count. Okay. Ha! Look at that. Let's try this. So, surprising. Okay, so you don't have to know this, but I just, as a curiosity. So, from sys import get ref count. So sys is a standard thing in Python, and get ref count is a function. And now let's say, okay, so let's actually create a new thing. So x is let's make x a list of A, B, C. Okay, so x is a list. So there's now a object called, there's some kind of PyObject here. The type is list. The ref count is hopefully 1. And the value is actually a list with 3 strings in it. And what are these things? These things aren't strings, they're PyObject that happen to have a string inside. All right, so I'm gonna have a lot of shorthands, but really the thing inside this list is a 3 PyObject. Each one of these PyObjects happens to be a type string and have a string object inside. I'm gonna draw them all out. So it has ref count 1 because somewhere x points to it. So now let's test if that's actually true. Okay, there's 3. So it's probably because there's some other things holding onto it as well. So Python has some stuff behind the scenes that probably holds onto it. But the important thing to recognize here not is the absolute number, but the relative number. So y equals x. So in Python, what y equals x does is it doesn't make a copy, it just points both to it. So when I say that, what actually happens is y and x now both point to this. And now this, it was 3 before, right? So now this ref count better be 4. Or else something will be really wrong. Okay. What? Oh no, x. That's really weird. Okay, maybe that's why they're putting this thread on. That's very strange. Maybe the get ref count doesn't do what we want. Okay, well, hopefully you get the point. But reference count is generally includes. Okay, so the count is generally 1 higher than you might expect because it includes a temporary reference as an argument to get ref count. Okay, but it still doesn't explain why they both. Oh wait, that just jumped up to 5. Wait, this is really confusing. Oh yeah, we can't access anymore. Okay, that was super confusing, but let's pretend like it worked, and that the ref counts increment and decrement. There's weird things behind the scenes in Python, as you can see, because other auxiliary things might be holding on the list. But as far as you're concerned, the ref counts work like you expect. Every time something points to it, it increments the ref count. Every time something doesn't point to it, it decrements. Yeah, that's why this person was confused. My ref count is puzzling to me. I closed Python, tried it again, shut off my computer. As I expected. Why? Let's see. Well, we can dive into the details here. Next to Python, few modules loaded automatically. Okay, well, alright, well that's that. So, okay, so let's keep building up what the objects have inside. So we have a ref count, we have a type, we have a we have the value, and we have the ID. So now actually let's go into the code itself. So we're going to go into Python 278 include, capital I include, and then we're going to look at object.h. This is a good segue into object.h. So recall that everything in include are .h files, so they're header files in Python. So header files usually define the specifications of either objects or functions. So they don't actually have code, they just have kind of declarations. So object.h, I'm going to use Vim as my browser, my editor. There's a line numbers on the left so you can follow along. Here. So what this file is it implements objects and object interface. So blah blah, we can read through this. Okay, there we go. Object is reference count, perfect, right? That is increase or decrease whenever. Whenever counts reference 0, it can be removed from the heap or garbage collected. So this is exactly your point. Object has a type. This is confusing also because the types themselves are also object. It's called a type object. So the type object also has a type, and it's called a type object, which is the type, which is super confusing. But everything's an object in Python, right? Like this is why it's like, so imagine I have a py int object. Inside there's a type. This actually points to a py type object. And this value is, it's an integer object or something. And this type, everything has a type. And this type goes to a py type object whose value is type or something. And it ends there. And then this, assuming this type thing just points to itself. So it just ends there. So everything's an object, right? So that there's no behind the scenes things. And because everything is an object, the operations are very uniform on things. So, like the pointer itself, right? Perfect. That's exactly what I said. So the type itself has a type pointer pointing to the object representing a type, which contains a pointer itself. This is the other important part. Objects do not float around in memory. Once allocated, an object keeps the same size and address. So that's why the ID is the memory address. So when you allocate an object, it just stays put in memory until it gets deallocated. It doesn't shift around. Objects that must hold variable size data contain pointers to variable size parts. Size cannot change. This is an important restriction here, you can see. So the reason why it doesn't move around, so that the references that you pass around, it's actually somewhat efficient because all you have to pass is the memory address or the pointer to that thing. It's guaranteed the object never move around. So if you're familiar with like garbage collectors in, say, Java or other languages, some languages use what's called a mark and sweep garbage collector, which actually, or a compacting garbage collector, which means that it actually moves the objects around as it garbage collects. So Python does not do that. It doesn't move the objects around after it allocates them. This means that it's easier to implement, the code is easier, but it also means that it's less efficient, right? Because your memory can get very fragmented. Because you have objects everywhere, they get deallocated, your memory gets super fragmented. As you can tell, Python is not optimized for maximum performance. It is optimized for readability, at least, right? Because this is how you would probably implement objects in the most straightforward garbage collection in the most straightforward way. It's very easy to implement a garbage collector for this because there's no moving or anything. Here is more, and I'm just reading the documentation out loud, it's pretty important. Objects are always accessed through pointers of type PyObject star. It's always accessed through PyObject. So notice that everywhere in the code is littered with PyObject star. The PyObject is a structure that contains only the reference count and type pointer. So this gets back to your question earlier of what is a PyObject. A PyObject is actually very thin. A PyObject only has type and ref count. So ref count's an integer, or an unsigned integer, I guess, and type is just a, some pointer to somewhere. So if you recognize this, the PyObject type actually is very small. It just has type and ref count. So how do people actually do anything with PyObject? You actually, every kind of object is a subclass of PyObject. So it actually is called structural subclassing. So if people are familiar with C, people kind of fake object-oriented programming with C by defining structures that look like the base class but are just extended. So example is, let's go, well, this may not be the real thing, but let's say that PyObject in memory, this is in C, right? In memory, PyObject just has two fields in it. The first field is called type. The second field is called ref count, or whatever it's called. This is just an integer, right? This is like 2. This type is a pointer, so I'm just going to say this points somewhere, right? But really in C, this is just a number. A pointer is just a number, but it just happens to be a number interpreted as an address. So what is a PyInt object? A PyInt object, there's probably more to this, but conceptually, a PyInt, I want to draw this on a cleaner slate, sorry. That'll look confusing. Okay, so this is how, this is called structural subtyping. And this is a concept that people do in C. So this is in C. So the PyObject type, every PyObject object you create in C has, let's say, two things, has two slots. One slot is called type. One slot is called ref count. And ref count is, 2, whatever, and type points something else. Every PyInt object you create, C has no object-oriented features, right? It has no inheritance, it has no anything. So when you make a PyInt object, the trick is that you want to declare a PyInt object so that the first two fields are exactly the fields in object, type and ref count. And then you're going to define additional fields down here. So I would just say call this value. I'm making these names up. So value is 500. Ref count is 2. Type is another thing. Type is a type object. And again, this thing has an object, a field type, ref count, and value, int or something. This is not precise, obviously, but and so forth. So all of these things are in the C world, right? This is all in C, in the interpreter. So notice how the commonality between all three is that if I try to access the first element or first field in any of these objects, I get the type. If I try to access the second thing, I get the ref count. If I try to access the third thing, I don't know what I'm going to get because it depends on the thing. So the key here is that I can actually use a pointer to PyObject, a PyObject star. In my C code, I can use a PyObject star to point to one of these things, one of these things, one of these things, one of these other things, and everything will work. And the reason why everything will work is because all a PyObject does is keep two fields, type and ref count. When I point this PyObject to a generic PyObject, we get type and ref count. When I point the PyObject to a PyIn object, hey, we get the same two things. It's all good. It doesn't know what's down here because a PyObject star doesn't know anything beyond the first two fields. As far as PyObject star is concerned in C, if your C code compiles, it can actually only access the first two things. Same thing here, only the first two things. Everything down here is whatever you want it to be. So it's in this way that we actually create a type hierarchy in C, even if though C doesn't have object-oriented programming or anything. So the type hierarchy is something like there's an object, a PyObject on top, and inheriting from this, there's a PyInt object, a PyString object, and so forth, right? So it's as though you're actually doing object-oriented programming, but you're in C. So in C, you don't have the convenient syntax of, say, something extends something in Java, or something, was it like implement something in C++, or subclasses, or there's some syntax for subclassing or something. But C, you can do object-oriented programming in C all you want. So there are libraries in C that implement full, more or less, object-oriented features. You can do this with methods also. It's astounding how bad code can get. Okay, so what's the point of this drawing? The point of this drawing is to go back to this code and to show how this is actually implemented. So there's a lot of macros here. There's a lot of macros, and here is, okay, so recall, so those of you who aren't as familiar with C need to brush up on the C knowledge, but what a macro is that it essentially expands, the compiler expands this macro into whatever. So I'm just going to copy and paste some things here just so we can blah.text. I'm just going to copy and paste a bunch of macros. We can expand it. There's PyObject head extra. And def trace extra in it. Okay, let's just ignore this. Okay, so you don't have to follow along. I'm just looking at this PyObject head. Okay, so good. Okay, so I just copied this code directly from the object.h. So define PyObject extra as blank. This means there's just no extra things. So I want to show you what happens when the compiler compiles this code. So this is a struct definition, or a structure definition in C. It defines a structure called PyObject. And notice how this thing says, this is exactly what I draw in the diagram before. Nothing is actually declared to be a PyObject, but every pointer to PyObject can be cast to PyObject star. This is inheritance built by hand. Every pointer can be, okay, so all a PyObject is that it has a PyObject head thing inside. So what is that? So we're going to look at our C code, and PyObject head is defined to be this thing. So this is what the C preprocessor does to compile this code. We actually call it preprocessing this code. I'm just going to manually do this. So type-def struct PyObject head goes to this. We're going to go into PyObject head. All PyObject head is this thing. So we're just going to, all a macro conceptually is, it just copies and pastes. We're going to replace PyObject head with this stuff. Okay? Now, this is another macro, PyObject head extra. So what is PyObject head extra? It's if you have this trace refs on for some debugging, PyObject head extra actually has some extra fields. Else, don't do anything. Just define it to be blank. Notice how this is actually this is, doubly crazy because this is actually an if statement in the C preprocessor. This means that if some environment variable is defined when you're compiling, make this field fatter or this thing fatter. If not, just don't do it. All right. So again, the compiler takes care of all this for you. For all intents and purposes, PyObject head is none. So define this to be, whatever, empty. So when I go down here and I expand this macro, this just turns into nothing. And let's erase this thing because it looks ugly here. And essentially, here we go. This is what we have. The PyObject, when it turns into C code, is exactly that, right? It has two fields. ob_ref_cnt is the reference count. It's of type PySize_t. I am assuming this thing is just some unsigned integer. So C has a great way of, nobody uses integers because for portability for other things, this PySize_t, I'm pretty sure, actually S means signed, I would say. So probably some number. This thing is a OB type. This is actually a pointer to a type object. All right? It's a pointer to a type object which represents a type. And that's it. That's a PyObject right here. So this this nice piece of code here is this right here. Makes sense. I named it differently, but that's this thing. But of course, you would never actually create a PyObject. You actually want to create a PyInt object. So let's actually look into PyInt object and see how that's implemented. And all the other ones will kind of follow from that. So let's go to, and there's just a lot of code here for rough count. Oh, rough count. So there's some macros here that are convenient for you, right? Wow, it's kind of bright, so you can't see it. Py_rough count casts the object into a PyObject, and it grabs the rough count field. PyType grabs the type field. There's actually a size. Oh, size is a var object. So var object is a variable sized one, like a list or something. But for basic object, it just grabs the type information. Again, these are just convenience for you, just so your code is a bit more compact. So whenever you see PyType, it actually grabs the type field out. And notice how it has to cast it to a PyObject to grab it out, because that's what it knows about. So let's look at int object now. So same directory, intObject.h. This is the interface for an integer object. PyInt object represents a long integer. This is immutable. Integer cannot change. There are functions to create this, do all this. So all this code is actually pretty well implemented, documented. So when you actually do your assignment, you can just look for a lot of reference. So this is actually probably the simplest object that you can find. This is great. So I'm gonna just copy this code here. So I'm just copying it into my blah file. Okay, so what is a PyInt object? A PyInt object is PyObject head. And what is PyObject head? It's this thing. So we're just gonna copy it down. And what is this thing extra? It's nothing. We just killed it. And there we go. We have that. So notice how a PyInt object is exactly the same. So that macro allows us to really easily put the first two fields the same in every type. So we don't have to because we could just manually retype it for everything, but that seems kind of silly. So notice how a PyObject is this structure with two fields. A PyInt object is elegantly the structure of the same two fields and an extra field. And this field is a long ob_ival. This is exactly what you expect. This is a long, which is a long integer, signed integer. ob_ival is that's the number that you're storing, right? So all a PyInt object is the exact same two things as a regular object with a third thing. That's the integer. So if we look back on this diagram, this is exactly what it is. Same two things, a third thing. This is just called ob_ival or whatever they call it. I just call it something different. And this thing is actually just a long integer. Does that make sense? So that's an int object, and we could do the same tedious exercise for all the other objects also, but it's going to be the same thing. So let's actually look at a string. String object.h. So, varhead. Okay, so this actually is a special kind of object called a variable size object, varhead. This the string actually is a variable size object, so it can actually expand. So it's a little bit more complicated. But let's look at a boolean. Bool. Wow, that. Huh. What does this even do? Pi false. Oh, what this is actually a boolean is just there's only two booleans, right? There's only true and false. There's only two that ever exist, and this just defines them right here. That just defines them as two integers, some true or false special integers, and it just uses those. So that's kind of a silly hack. Okay, so let's go. We'll spend the last 10 minutes or so going into the implementation. So cd out, go to capital objects and object.c. And this is the all the generic object things that you can do with objects. So recall C code is actually the actual functions. There's a lot of stuff here. I mean, we're not going to go through all of it, but let's look at one that's, I'm trying to find one that's informative. A lot of these are just debugging. Inc count. These are all debugging. Dec count. Let's find one that's actually, so inc ref, dec ref. So these are decrementing reference counts. Init. Yeah, these are all just internal things. PyObject new. PyObject. So if you're curious about how memory gets allocated, when you create a new object, it actually you need to pass it a type. So I want to say I want to make a new integer. I want to make a new string. You actually pass it a type, which is integer string, so it knows how big to make it. It actually uses malloc, which is the C function for allocating memory. This is a special malloc because it wraps through everything. This actually allocates new memory, puts it in an object, and just initializes it, calls a constructor, and returns it. This is standard object initialization. We're going to have you go over this in the assignment a bit. But new variable, delete, print. A lot of these are things we're not caring about studying because this is just like how do you print out an object. There are a lot of code that's not very interesting. I'm trying to find one. REPR. Okay, STR is a decent one. It's actually pretty big. I'm trying to find str pystring check console. Okay, let's just do this one right here. So PyObject_str. So what this does is that every object can be converted to a string, more or less. So let's say I have, x equals 1, 2, 3. So str is a function that you can pass into anything, and it'll turn it into a string. And it's especially useful because the reason why it's kind of built in, it's useful is because you can print stuff out that way, right? When you're printing a date or a, so let's import. So D is some kind of a special date object by strd. So notice how if I call str on D, it prints it into a somewhat nice looking string. The reason why this is useful is because when you call print, it will convert stuff to a string and try to print it out for you. Or when you want to, basically printing, right? You want to convert to a string. So the question is, how do we actually know how to, I'm going to just call it directly like that. That's a list I convert to a string. This is a dictionary I convert to a string. This is a string even convert to a string where it doesn't do anything. This is an integer I convert to a string. You basically convert everything to a string. So what this conceptually does is when you call this str method, it will look inside of the object and see if it implements a converting to string thing. And if it does, it will actually call this code. So this is the most generic code for converting something to string. So at this point, it doesn't know what type of object it is. It just knows it's an object, and we can convert it to a string, maybe. So what it does is it just calls this internal function, PyObject string, which jumps here, just a few lines up. And all this thing does is that it just tries to, it tries to find the type. If there's nothing, we just say null. If there's actually a string inside, we can enter recursive call string check. Yes, this code is actually not super interesting. TP string. Okay, actually this is the most kind of juicy part of here, this line. So what this says is that this converts this pointer into the type that it's supposed to be in, and it looks up a TPSTR method, and it calls that method on V. So TPSTR is a method that all things that can be converted to strings implements to convert something to a string. And this is where the dynamic aspect comes in. So if I call this, remember this is completely generic, right? For the rest of this lecture, this is completely generic. This is just an object. When I call this though, this is the thing that jumps into the specific code for each type. So for example, a list object has some kind of a TPSTR method in it that will know how to print the whole list as a string by going through the list, putting the quotes, putting the brackets stuff. A dictionary object has its own TPSTR thing. An int object has its own thing. Everybody has its own thing. And this sounds very much like object-oriented programming, right? It's one particular interface called TPSTR, and every particular type implements its own version of it. And this is where it actually dynamically dispatches into which one to call. So if I ask you, where does this code jump to? There's not a good answer unless you know what the type of V is, right? If V is an integer, PyInt, it jumps to the PyInt version. If V is a string, it jumps into the string version. So it's impossible by just looking at the code to tell me where the code jumps to. And this is for a reason, is because we need this str method to work for anything, right? We need to work on a number. We need to work on a string. We need to work on a dictionary. We need to work on a list. We need to work on everything. But the kind of high-level point I'm illustrating here, we'll get into the details in Monday's lecture about the different types, is that this is all very vague and abstract point. It's just that everything goes through this generic PyObject.c this object.c first, and then it goes to the specific thing. So there's a lot of code to it. Basically, whenever you do an operation, let's actually go back to our whoa, this is kind of messy. Let's go back to our operation of x is a number 1, y is a number 2, and all we want to do is say x plus y, z equals x plus y. Right? That's all we want to execute. It seems so straightforward. We just want to execute this. So what is it in bytecode? This is a pretty simple piece of bytecode. We'll just write simple.py, x equals 1, y equals 2, z equals x plus y. It's just this piece of code right up here. I'm just going to run it. Obviously it doesn't do anything because it doesn't print, but dis simple.py. So this is the bytecode for reviewing for the new students here. It's you load a number 1 stored in x, load a number 2 stored into y. That corresponds to x equals 1, y equals 2. This line is you load x and load y, add them, and store into z, and this corresponds to z equals x plus y. And it's a long-winded way of saying, just add them together. So what the binary add does is that it actually looks up and calls the add operation on x and y. And conceptually what happens is it goes through the interpreter, it sees that there are 2 objects on the stack. So at the point the binary add is called, the stack actually has 2 things, a 1 object and a 2 object. And the interpreter tries to call binary add on them. So I'm just going to zoom in here in detail. There's a 1 object, which is a PyInt object, whatever, that happens to have a value of 1. And then the 2 object is a PyInt object, or whatever, that happens to have a value of 2. And what the add operation does is it has to go inside, grab the 2, make 3, put a whole new PyInt object, and then assign it to z, right? So conceptually where the control flows is it goes to the interpreter, it interprets the bytecode, and then it actually jumps to a generic object binary add thing, and then it jumps back to the integer version. So let's actually spend the last minute or so looking at this. So for those of you who are new, the main interpreter loop is in Python c eval.c. This is a giant file that you have to go through. So is it binary add? Ah, it actually does a fast case. Okay. So it actually is optimized, right? So this case actually, if we know that they're both ints, which is a common case, we actually just simply grab out the integers and then and just add them. We have to do this check though, because when you add two things, they're not necessarily be ints. What if they're points or people or money or something? It's not necessarily the case. So this is actually an optimization. Same thing, string, string. If they're both strings, it concatenates the strings together. Otherwise, it does a numeric add operation on those two, and we jump into that code, it will probably dispatch everything. So actually, this did unfortunately not illustrate on point because it actually directly just grabbed the integers out, which is what you want it to do. But in general, I think this code could be written to do a generic add on both of them, which will call the objects add, and then those will dispatch into the add of each type. But because integers are so common, it's actually just built in.